Design for assembly is a specific design for X method that looks at ways to reduce the assembly cost. When you look at assembly systems, manual or automated, what we're concerned about is the total dollars we're investing per assembly. And as you can see here, with a manual method, we have a fixed unit cost, which doesn't change as the production volume increases because it takes the same amount of time to manually assemble that product. Versus an automated system, which, as we see, the cost is decreasing, and that's a direct result of the fact that we're able to keep up with the demand up to some point in time. And again, we show that decreasing until we reach some production volume at which we have to purchase more equipment, and then our cost is going to go up, and we're going to see this zigzag kind of curve here. So you can see there's a trade-off point here at which going with an automated approach will be a better idea than sticking with manual. And really that's based on your total production volume, which we'll see throughout the semester as a major variable in our manufacturing system. Well, the design for assembly technique comes in a variety of forms. It can be customized based upon individual companies. It can be proprietary with that company. Popular methods for, and they're all very similar with slight variations, include the Boothroyd and Dewhurst approach, the Lucas approach, and the Hitachi assemblability evaluation. Again, what they're trying to do in all these methods is to go back to the notion of a part family and use group technology methods to group by shape and type of part. Again, in these methods, don't forget, these are estimates only, and we're not trying to accurately predict various characteristics of our product. We're trying to estimate the assembly times, and these are going to be fairly crude estimates, which you've had experience with in using products like MOST based on time and motion study. The goal here is to identify redundant parts or parts that can be targeted for redesign in order to come up with a minimum number of parts, which we've already seen as a fundamental principle of design for X, and reduce the number of repositioning, refixturing operations, which is consistent with top-down assembly, and any part consolidations or modifications to part features that will simplify the design. So that's the basis. Here's a nice example from Redford in the design for assembly text. If you look at the pump assembly here, we have a classical piston pump where the fluid is entering the pump at the bottom, passing through a filter, and so when the piston moves upward, the fluid here will unseat the ball, and now we have fluid moving into the chamber here, and obviously as we move the piston further up, we're going to pull in even greater volume. And then when we push the piston down, of course this ball will seat against that and essentially acts as a check valve to prevent fluid from flowing out through the bottom. Then this ball here is going to unseat if we have enough pressure to overcome this spring, and then we're going to have fluid moving out through this outlet to wherever it is it needs to be. Of course, this O-ring is providing a seal for the body against our base. And then, of course, the shaft, which goes through the body here, is going to be attached to some driver motor that is going to cause the piston to reciprocate here. If we look at this, it's fairly obvious. We've got a bunch of pinhead bolts that are used to attach the body to the base. There are washers involved. We have some nuts, and there's also a retainer to keep the ball here from leaving that area. So how can this be redesigned to eliminate parts and consolidate? Well, after their redesign, you can see there's been a significant change here. First of all, we have snap fits, and these snap fits allow us to remove a lot of the fasteners. You can see the snap fits on the base here. And so the body is going to snap into that. We've got kind of an edge here that will catch that snap and provide a seal. The piston material was changed, so now we no longer need that O-ring. And the valves have been greatly simplified. As you can see, there's no ball and spring, and we replaced that with essentially 2 new valves here. So we get a reduction in the number of parts. You can count up the number of parts, so this will greatly simplify the assembly as well as the cost, because you've reduced your holding cost, the number of parts that you are storing in your facility. So how do we go through that kind of a process to get from that initial design to the less costly design? Well, you need to start, first of all, with the product specification. And we'll talk about this in the context of doing some type of manual assembly. Product specification, as we know, tells us the actual components and their dimensions. We might have a prototype, a working prototype of the product. We might have the actual product itself, and we're trying to improve upon its design. And then we need estimates of assembly operations. And so that will vary from method to method, depending on how those estimates were arrived at. But they will be based upon characteristics of the product specification, as you'll see. So let's look at a popular approach, the Boothroyd and Dewhurst method. Here you identify the individual parts that you're going to analyze, and that will correspond to the bill of materials, which you're already familiar with. Then we'll determine a feasible sequence, and let's just note here that potentially there are thousands of feasible sequences. So if I have n parts from my bill of materials, then an assembly is essentially a permutation, and as you know, a permutation gives you n factorial ways of combining those individual items. So it can quickly get out of hand in terms of the number of possibilities. Of course, this is the upper bound, n factorial. It also has to be feasible, and by feasible we mean that we cannot violate any geometric constraints. For example, let's go back to that pump. Clearly, in the pump example here, we will not be able to attach the body to the base until the piston, the shaft, the bolt attaching the piston to the shaft have all been assembled. So that eliminates certain sequences in this context. So every part that you're putting together here is going to have some type of constraint which will reduce the number of feasible sequences. If you have parts with multiple occurrences, of course, you'll determine the number of consecutive assembly operations. And typically, this is going to be a set of fasteners. So for instance, if I've got a bracket and it has 6 bolts, which are exactly the same, and 6 nuts, then we're going to make them consecutive operations. Next thing we do is estimate the handling time, and this is really prior to insertion. So everything we have to do prior to adding it to the assembly, and then we follow that with an insertion time. So altogether, this will account for the total assembly time for that individual component. And then, of course, we can estimate the assembly operation time. If we know what it cost us per unit time, then we can estimate also the cost. And then we can assess the minimum number of parts in terms of the theoretical lower bound. And Boothroyd and Dewhurst propose a design efficiency criteria, which is supposed to be a measure of how effective your design is. And then the process can be repeated and iterated, and hopefully it converges rapidly. So let's look at this metric that was proposed by Boothroyd and Dewhurst for a second. Don't worry about the numeric value of 3 here, but let's concentrate on this ratio. So they're calling the design efficiency the ratio of the theoretical minimum number of parts to the total time. So just for argument's sake, let's say we reduce it down to one part. Then the question is, what is the denominator? So in terms of efficiency, the design is going to affect the total time it takes to assemble that. So how complex is the part in terms of being able to handle it, being able to insert it, as well as the total number of parts that are going into the assembly. So if you look at this ratio, it's really estimating some type of average assembly rate across all the parts. Now, clearly, when you're thinking of this from a throughput point of view, in terms of production rate, we would say let's maximize this ratio because we want to be able to produce the most parts in a fixed amount of time. And so we could argue that the larger this value, then the more efficient the design is in terms of your assembly system. The parameters that go into this estimate of our time and cost are, first of all, the number of consecutive operations. If I have the same part and I'm adding a number of them, then there's going to be just a factor that will multiply by the handling time and insertion time. Again, where does this information come from? We're going to have a database of values that we can rely on based upon the characteristics of the product that we'll talk about a little bit later. Well, then we can calculate the total operation time for that assembly and the total operation cost. Of course, if you're going to have cost, then you need to have some idea of your direct labor rate in dollars per unit time. So the estimate is very simplistic. Here's our operation time, number of consecutive operations. It'll be from 1 to however many parts we have that are identical. And then we add up the handling and insertion time. Our cost is based upon our direct labor rate times the time, and then of course we have to convert from seconds to hours. So these time estimates are typically in units of seconds. Well, how do we come up with the handling and insertion times? What Boothroyd and Dewhurst proposed was to come up with some way of characterizing the product in terms of how it affected assembly. And it's not going to be exact, but it will give us an estimate of what the assembly time might be. So what we're trying to do is categorize in a very rough way how parts are similar and how they're different. So as you can see, the handling parameters that they propose have to do with the number of hands that the operator can use, 1 or 2. If a grasping tool is involved, which typically means you have a very small part. Also, if we have to have some magnification, microscope, and so forth, that makes it more difficult. Or if it's just a part that's difficult to grasp or manipulate, and that's really a judgment of whoever is performing this evaluation. The weight of the part will definitely affect your ability to handle it. If it has some symmetry to it, and the size of it, and the size is phrased in terms of thickness and a size parameter that we'll look at in just a moment. What is this rotational symmetry during handling? Well, think of it as if you have a part and you are moving it in terms of the insertion direction with the product, and that's what this vector represents. So I'm moving the part in the direction of where I'm going to insert it. And now I think about rotating about that vector. So that represents what we call beta, and it's about the axis of insertion. And then we'll create an arbitrary axis perpendicular to that and think about rotation about that axis and call that alpha. Note, of course, we don't have a 3-axis system. We're only dealing with 2 axes, so it's giving us a rough idea of part symmetry. Now, what are the actual values of alpha and beta? Well, you think of the smallest angle that you can rotate the part and still insert it properly. So, for instance, if I have a cylinder and it has to seat in some feature here, my axis of insertion is in this direction, and so beta if I were to rotate this 90 degrees about the axis of insertion, beta equal to 90, it would still insert. And if I keep reducing that, beta equals 10, beta equals 1, beta equals 0.1, you can see beta approaches 0. So when I have symmetry like this about an axis, then beta will always equal 0. Now I look at alpha, so I'll make an arbitrary axis here perpendicular to the insertion direction. And as you can see here, if I rotate it 90 degrees, then I'll have a cylinder oriented like this. And clearly that is not going to seat in the feature here. So I'm going to have to rotate it an additional 90 degrees, which tells us the minimum angle by which I have to rotate that and still be able to insert it will be 180 for alpha. So now I've got a measure of symmetry for this part. Beta is equal to 0, alpha is equal to 180. Now, when is alpha equal to 0? Well, you can think of a sphere, for example, the ball in the pump example. We can rotate that any alpha, any beta, and it will still insert in the feature here. So a sphere, that makes sense, it's the most symmetrical object, and therefore alpha equals 0 and beta equals 0 are consistent with this notion of rotational symmetry. The other thing that we're concerned about is the size of our part, but we're not going to use the individual part dimensions. We're going to come up with an estimate of the size by taking our part and placing it in a box. So think about a box that we can contract around the part to find the smallest box, and it will fit inside that box, and then we'll look at the box and say, okay, the thickness will be the shortest side, and what we call the size will be the longest side. So again, it's an inexact, but it gives us a rough idea of how large the part is based upon the part dimensions. For the insertion parameters, once we have our handling parameters, we can look up the time for handling. We're looking at some other considerations. First of all, the securing of the part. Now, when you think of securing the part, what happens when you release the part after you've assembled it into its location? Does it tip over? Is it going to be secure? If the assembly is bumped, will there be a problem? Another important aspect of inserting a part is accessibility. How easy is it to get it to the location where it needs to be assembled? And from an operator viewpoint, the line of sight is extremely important. So if you can't see where the part is going, it makes it very difficult to assemble into that location. And then just a general assessment of how difficult it is to position and orient, because there might be other parts around it that make it difficult to get it into the right position. After we insert it, is it going to maintain its position? Is there any resistance when we insert it? And is there threading involved? As we've seen, threading is problematic. This is going to take additional time if we have threads. Also, is there any plastic deformation, which means a permanent a deformation of a part that causes some type of change in the surface? Once we have our times from handling and insertion, then we fill out a table here and place those times into the table. So you can see we've got a spreadsheet, and we can easily calculate all our parameters. So we end up with our total time, the cost, and then our design efficiency once we come up with a minimum number of parts. So this is the question, and that is, once I've got all of this filled in, how do I estimate the minimum number of parts? So there are three questions that we're going to ask in order to do that. First of all, relative motion. So we've already seen that in the design for X principle. Does the part move relative to other parts that were already assembled? If it does, then clearly we cannot combine it with other parts. And is it of the same material? Because if we have to use a different material, then it cannot be combined easily with other parts. And then we think about disassembly or maintenance. Does this part require frequent maintenance? If you said yes to any of those, then it's indicating that you definitely need that part to be separate. And so you would enter a 1 in your spreadsheet there. So that's how we make that determination. Now, of course, that's assuming there's only one part. If we have 4 bolts and we need those 4 bolts, then obviously we're going to have 4 parts there. So if, again, the answer to any of these questions is yes, then you need that part to be separate, so that will form the lower bound of the number of parts that you need, and now you can calculate your design efficiency. So basic rules here for design for assembly: reduce the number of parts based upon what we just saw in that analysis. We'll come up with that theoretical minimum number of parts. The ones that have zeros, that indicates that we can eliminate them. We should also try to eliminate any necessary adjustments if we can change the design. For instance, if we've got to adjust the height based upon some movable locking fastener that allows us to adjust the location of a part up or down. We also need to simplify handling based upon those handling parameters and any alignment of parts as they are being assembled. If there's a way to provide easier access by changing the geometry of features, then that will also help decrease the assembly time. So in summary here, what we're trying to do is relate what we see in the design specification in terms of design parameters to these characteristics of the product that affect other stages in the life cycle, such as assembly, which we just looked at. If we can characterize that, then we might be able to improve upon the design, either through models such as the model that we had for design for assembly, or simulation of some kind. What we need to perform this analysis is the product geometry and material that's being used. The output will be the identification of some new geometry that might be advantageous, or any material problems that we would want to resolve. Again, these types of methods typically do not tell you the solution. They're only describing what the situation is currently in terms of the assembly, in terms of ease of fabrication and other aspects of the design. So the solution is yet to be determined, perhaps because you're not sure how those parts will be combined, you're not sure how the features will be modified, but you are identifying the potential for improvement on the design, and the bottom line is it will help you be more competitive because it will reduce your overall cost.